Is it the usual? Hello?
Actually,
Yeah.
we are still catching up with your notes and with the uh, with the basic contents are like, even for
Okay.
example, the differentiation and integration also sometimes
Mm.
it's taking some time to recollect and
Mm. So what can I do from
stop.
my side? Don't
Um,
teach is one option. Is there any constructive option or?
um, no, actually, action item is from our side only. Is what I mean. At least for me, it's like I need to spend a little more time to
So
revise
that I
these
agree.
things.
So all the students who are working in, so they will first of all lose touch with the basics. Secondly, they'll also be busy during the week, so they'll not get perhaps much time to revise it. So that part everybody has. So is there anything I can, if there's something I can do, please let me know. So otherwise, shall we start the lecture or should I cover something which I already covered again or
Um, yeah, maybe I think it would be useful if you could summarize the last lecture's content, sir.
okay, okay, fine.
Thank
So
you.
that I'll do. Okay. So in the last lecture, we talked about the following problem. There is some unknown likelihood, P star, right, from which you have collected M's independent samples. So let's say, and then the goal is to reconstruct or estimate P star, right? And we broadly looked at two ways of estimating P star. Uh, by the way, so first of all, to estimate P star, we assume a model again, like in case of non-probabilistic modeling. We had the inductive bias. Like that, we also have a choice valid set of candidate likelihood functions. So this is nothing but the set of candidate likelihood functions. So, and our assumption is that P star belongs to this model. Okay. So then the problem turns out to be picking one of these candidate likelihoods. So the question then turns out to be which of these likelihoods functions is closest to P star given the data. So that's the question you try to answer. And then we said we'll usually go with parametric model. So where if I pick a parameter, then I'll be pick a parameter set of parameter values, then I'll be picking up a particular likelihood function. So as the parameter values change, the likelihood functions change in the model. So that's what, and we call the parameter as say theta. So this theta itself could be a vector or something like that, right? So the standard example for model is say Bernoulli model or Gaussian model, which is nothing but a set of all Bernoulli likelihood functions or Gaussian likelihood functions, say. And in case of Bernoulli likelihood, there is only one parameter, which is probability of heads or probability of 1. And in the case of Gaussian likelihood function, there are two parameters, the mean and the variance, right? And in the general multivariate case, it is the mean vector and the covariance matrix, right? Okay. So That's what is the model. Then the problem is to estimate the right parameter. And so there are, we said, two main ideas in parameter estimation, and essentially both of them simply differ in the way they say how two likelihood functions are close by. So the last function they use are different. That's all we said. And one of the method is called as method of moments, and the other method for parameter estimation is called as maximum likelihood estimation. In method of moments, the way you estimate theta is you say, I'll compute the expectation of some function of the random variable psi, under which distribution, under the distribution specified by the theta parameter, and we'll equate it to the sample version of the same moment, right? So this is what is done in method of moments. So it is simply a expectation match, and we commented that the usual choice for psi will be such that it will be easy for me to retrieve the parameter values. For example, if the model was Bernoulli, then I would choose a psi function such that my expected psi value will simply be the parameter, which is the probability of heads, right? So we consider this function, right? So psi of x is equal to indicator of x is equal to 1 or heads, whatever, right? So then expectation of psi of x under parameter theta will simply be expectation of indicator of x is equal to 1, which is simply probability uh, of x is equal to 1, which is simply theta. If the distribution is parameter, the parameter is theta, then this is simply probability of heads. Then the other example we gave was maybe the multivariate Gaussian. We also gave the univariate Gaussian, but just to revise, let me do the more complicated one again. So the multivariate Gaussian. In this case, the parameters are the mu vector, which is nothing but the vector of expected values of the individual random variables in each dimension. That's what is mu. And sigma is nothing but the matrix of covariances. So so basically mu I is given by expectation of xi, and sigma ij is given by expectation of that's the definition, expectation of xi uh, minus expectation of xi into xj minus expectation of xj. So that's called the covariance between xi and xj, right? So those are the entries in the covariance matrix. So then we said the obvious choice for the psi function will be such that you retrieve each of your mu values and sigma values. So here is the exact psi function we chose. So the first one will give you expectation of x1, second will give you expectation of x2, so on. This will give you expectation of xn if there are, it's an n-dimensional vector. And then the next choice will be x1 minus expectation of x1 times x2 minus expectation of x2, right? And so on and so forth. So for all, so this is say xn minus 1 expectation of xn minus 1 into xn minus expectation of xn, right? So why this choice? Because when we consider the expected value of psi function at parameter theta, mu and sigma basically, that will be simply the expectation of x1, which is nothing but mu1, then expectation of x2, which is nothing but mu2, and expectation of xn, which is nothing but mu n. Similarly, expectation of x1 minus expectation of x1 times, you know, x2 minus expectation of x2. This will be simply sigma 1 2 and so on, right? And what will this be matched to? It will be simply matched to the empirical version of. So this is what method of moments does. It simply computes the average of all these. So average of this is simply, you know, 1 by m I equal to 1 to m x I1, right? So which is nothing but the first attributes value for each sample I taken, you know, I take an average. And similarly this value will simply be 1 by m sigma ij xi. Oh, so this is already 1 2, right? So xi1 minus, you know, this is mu1 into xj, sorry, this is over sigma over I only, xi2 minus mu2. So this is nothing but sample covariance, right? So this is sample covariance, this is sample mean. So this is the true mean and this is the true covariance. So in method of moments, what are we simply doing? We are simply saying we'll estimate the true expectations by the sample versions of the expectation. So very, very simple algorithm, right? So be whatever, you know, distribution it is, this is the kind of matching we will do. The only clever thing is how do you choose this size, and you choose this size such that you simply retrieve your natural parameters. Okay, okay. So this is the first method, which is called method of moments. And the second method is what we called as maximum likelihood estimation. There the idea is you use the loss function as the KL divergence, which then leads to the following optimization problem. I'll try to
Sir,
get that. Yeah,
sorry to interrupt you, sir.
yeah, no problem.
Actually, you said method of moments is basically about estimation of true expectation. So
So this is the, yeah.
averaged over all the samples.
Yeah, so you basically equate the true expectation to the average value of the same function, right? So if you are
Okay,
trying to estimate expectation of x square, then you will equate it to average value of x square. That's all, right? So that's what this equation is saying.
okay, okay.
The only question is that which psi function will you use? Will you use x or x square or some other function, or so that depends on the distribution. For
Distribution.
Bernoulli, you would use, you know, this blue highlighted function, not x, not x square, right? Why? Because when you use this funny function, you will retrieve the parameter directly, right?
Okay, okay.
Expectation of this will simply be the probability of hits. Similarly,
Yeah,
in
yeah.
case of Gaussian, you use this, you know, particular, you know, funny vectorial function. Why? Because when you take expectation of x1, it will be simply mu1, right? That's the first expectation, so on and so forth, right? So this will be the
Okay.
so some ijth fellow here will be the ijth covariance, right? So how is I selected? Simply based on whatever is your, you know, parameters defining your this thing, right? So this can be done as long as your parameters are like expectations. But in some distributions
Okay.
you may have parameters which are some functions of distributions. For example, I don't know if some of you have you know, revised the second chapter in Kevin Murphy's book. If you have revised, then you know, they'll talk about various example distributions. One of the distributions which they talk about is beta distribution. Now beta distribution, so by the way, this example is only if you have revised. If you have not revised, just, you know, just ignore this example. Beta distribution has two parameters, A and B, and none of them are expectations. So actually the mean can be written as a function of A and B, and the variance can be written as function of A and B. In those cases, you will basically write, you know, these formulae and then solve. None of these expectation of psi will directly be the parameters, but there will be some function of parameters. For example, in case of you know, beta, it will be some function of A and B, right? So you will solve, you will have some equations like g1 a and b, gn a and b, some functions equal to some values alpha 1 to alpha n, right? You will estimate a and b from, you will solve this system of equations to get a and b, the parameters, right? Right. So that's basically how you go about doing it. So there's no one answer for which psi function do you choose. You choose psi based on your convenience, right? You, the only restriction is that you should take clever, you should take rich enough psi functions such that all your parameters are estimated. Suppose I choose psi function as the uninteresting function 0, right? Then none of my parameters will be estimated, because this equation will be true always. So this blue equation will be true always if I choose psi function as the constant 0 function, right? So unless you go with such useless choices, any choice where you can retrieve all values of the parameters, that is good enough. Yeah. So did I answer your question, or if I deviated, I can get
Yes.
back to your question?
No, sir. I understood.
Right, right.
Thank you.
So essentially, this is what will happen. In method of moments, when you will have to solve a system of equations. And if you are clever, the system of equations will be very simple, like this. Here, what are you saying? Mu is equal. So this is just a vector is equal to another vector. What is there in solving? Solving is simply matching the individual entries, right? So, but in a general case, you could have a complicated system of equations which you should solve, right? So I'm not saying always method of moments will be simple. It will be simple if you choose a clever psi function. That's what I'm saying. And for most of the standard models, this anyway, will not go much beyond the standard four or five models. So for them, I have already told you what is the psi function, or you can refer the books. So half part of the story is done when I discussed about method of moment. The other half is, there's another method which uses a slightly different loss function for saying two likelihoods functions are close by, and the way they say that is by using the notion of KL divergence. And when we simplified the optimization problem, it turned out to be that we have to maximize the following likelihood function. So following objective. So this is what turned out to be the right. So just sum of the log of the individual likelihoods, and we said that this is also same as, this problem is also same as finding the maximizer of the likelihood of the data, right? So here p theta is the distribution. Okay, and this is intuitive because you are saying of all the choices of distributions, likelihood functions, pick the one which gives you the maximum value for likelihood of the given data set. So it's also intuitive in that sense, but we also gave a derivation in the previous class. Nevertheless, what we saw was solving this optimization may not be easy. So method of moments, at least you will have to only solve a system of equations, and that too, if you are clever, it will be a trivial system of equations that you have to solve. So most of the time, method of moments, computing it, estimating the parameters will be simple. But maximum likelihood, if you have to do the estimation, you will have to solve such optimization problems. And in the last class, I gave you an example of Gaussian where it was not trivial to solve the corresponding MLE equation. But nevertheless, what we observed is something interesting. Both maximum likelihood and method of moments gave the same estimates for the parameters, right? And I also commented that try going through your Murphy's book derivation for multivariate Gaussian MLE estimation, right? There it will be even more complicated because your variables will be vectors and a matrix, and the matrix has to be positive definite, right? So it's an optimization problem with positive definite constraints, and perhaps you will have to take derivatives with respect to a positive definite matrix and so on and so forth. So things get a lot more technical and cumbersome, especially if you are not familiar with multivariate calculus, or optimization in general. This will be a difficult exercise. Okay. So in this course or in exams, I'll not ask you questions which are, where variables are matrices or, something like that, complicated like this. And you will have to take, gradients with respect to a matrix and so on and so forth. I'll only ask perhaps very simple, simpler questions like the MLE estimation for univariate Gaussian. That I may ask in exam, right? But not multivariate. But the derivation is in the book. And the book derivation will again retrieve the same expression for the parameters. So the mean estimate will again be sample mean, and the covariance estimate will again be sample covariance, right? Okay, so this is what we have done in the previous class. So in short, we have given a way of estimating parameters for this problem where you have an unknown likelihood and you have samples from it. We gave a method for estimating parameters. We gave two methods for estimating parameters. One is method of moments and one is maximum likelihood. Both of them typically give you the same estimates, and method of moments is more often the easier one to estimate, right? Okay, so this I have revised the previous lecture. If you have any doubts, comments, if you want me to repeat anything, I can do that. Otherwise, we'll see how such parameter estimation will be useful for coming up with a generative model for regression and a generative model for classification. That's what we will do now. So
Sir, so in
yeah.
we are still talking about the x will actually be the output variable
No,
and
yeah, correct.
both
X
the
could be x comma y. Yeah,
okay.
x comma y I'm calling as x. That's all.
Okay.
It does not matter what is the form of x. Whatever it is, this is the idea. So any other doubts or clarifications?
Sir, I have a doubt.
Yeah.
Like in case of the univariate problem, like we will have only a single psi function, but when we are dealing with some
No,
multivariate,
even in univariate, there are two parameters, right? So if you remember, the psi function was again, right, x and I think x minus expectation of x. This is what we took as whole square as the psi function. Because with this choice, my expectation of psi of x will simply be expectation of x and expectation of x minus x square, right?
yes.
Right. So then I will simply, so this is mu, this is sigma square, right? That's why we choose this as a psi function. So psi function need not be scalar if your distribution is univariate. This is the counter example.
Okay. Okay, sir. And
Okay.
sir, like if we have more than one variable, like some function is like a Gaussian distribution, some x values, and the other one is following a Bernoulli distribution. Then in those scenarios, we will
Ah,
have two different psi functions.
right, right.
Okay.
How to deal with that we will do later. Okay. So that
Okay,
such
sir.
a
Okay.
situation will come in classification.
Okay. Okay.
So how to deal with that we'll see in classification. Okay.
Okay, sir. Yeah.
Yeah.
Thanks.
So nice question. Any other doubts, please? Okay. See, currently I have just given the overall problem description with possible choices for algorithms and some examples, right? So we'll see as we see more examples, it will be more clearer. Okay. So shall I proceed with the content of this lecture?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So now what we will do is, using the parameter estimation procedures which we have learned, we'll try to come up with a generative model for solving a regression problem. Okay. So let me recall for you what's the regression problem. A regression problem is a problem where the output space is uncountable. And let's take a particular example where the input space is Rn and the output space is R. That's a specific example of real valued regression problem. And let's assume somebody gave us the, there is some unknown distribution B star. So again, just I'm repeating x comma y, and you have samples from x1 y1 to xm yn, right? M samples, right? Now your goal is to build a generative model for solving this regression problem. Now how do you go about doing it? So please recall that there are three main steps in doing generative modeling. The first thing is you will model the, so the first step is you will model the entire joint distribution, underlying joint distribution of inputs and outputs, right? And the first step finishes by estimating the parameters of such a model. Okay, so after the first step, you will basically have an approximation for the underlying joint distribution. That's the idea, right? And what's the second step? The second step is basically from the joint you will compute the posterior, and the third step is actually the regressor, the final function, prediction function, which is the approximation to the base optimal. In case of regression, what it is? What is it in terms of the posterior? Anybody recalls?
It's the mean.
Very good. So it's simply the mean of y given x, right? Okay. So you simply have to compute the mean of the posterior. Okay. So these are broadly the three main steps. So let's go through each step in detail. So the first step is 1A. So the question now is, out of the four models we saw in the last class, what are the four models we saw in the last class? One is Bernoulli, the next is multi-Nolli, its generalization. Then we saw univariate Gaussian, then its generalization multivariate Gaussian, right? So out of these four choices, suppose I ask you which is the model you are going to employ for a regression problem, what will be your answer?
So multivariate Gaussian.
Very good. So the obvious answer is, the clear answer is multivariate Gaussian, because I mean, whatever is the distribution, the values the random variable takes should be in which dimension? Here, what is the random variable? It is x comma y, right? So what is the dimension of that?
You need
N plus
plus
1.
1, right? So, and n is at least 1, right? So at least the dimensionality of what we are talking about is 2. So we are at least talking about two-dimensional real vectors. So out of all the four distributions, there is only one distribution which outputs two-dimensional, three-dimensional, four-dimensional vectors. What is that? That's multivariate Gaussian, right? So that's a clear choice. So let's employ that. So our choice is multivariate Gaussian. That's very clear. Now what are the parameters for multivariate Gaussian? The mean vector and the covariance matrix. Then what is the next step? Next step is parameter estimation.
Sir, we could not hear you for
Hello?
a while.
Right.
For last 2 minutes, we
So,
couldn't hear you.
right. So I just said the obvious choice for the model is multivariate Gaussian. Its parameters are the mean vector and the covariance matrix. The mean vector is of size n by 1. The covariance is of size. Sorry. What is the size of the mean vector? Anybody? What is the size of the mean vector? Just to make sure you are on.
N plus 1.
Very good. So it's n plus 1 times 1, right? That's the. And what is the size of the covariance matrix? Anybody?
N plus 1 cross N plus 1.
Very good. Okay, so that's just to make sure at least one of you is awake. Okay, so sample covariance, right? Okay. So we are done with the first step. So essentially it's, the last class helped us to solve only one of the steps of generative modeling, the first step, right? Okay. Now what do we have after first step? After first step, we have an approximation for the underlying joint distribution in terms of the parameters mu hat and sigma hat. Okay.
Sir, it's
So
n plus 1 cross n plus 1, no?
yeah. So I wrote it. Okay. Yeah. So okay. So this is fine. So after first step, you have this estimate for your joint distribution. Is everybody with me till here?
Yes, sir.
Yes, sir.
Okay. So just for convenience, let me drop the hats. Okay. So wherever I write mu, otherwise things will become cumbersome. The notation will be cumbersome. So I'll just remove the hat. Is that fine? Hello.
Okay,
Yes,
sir.
sir.
Yeah.
Sir, why did you remove the hat?
No, it's just a notation. It is hat only. I'll write mu. You should understand it as mu hat because
Oh.
it will difficult. It will be difficult for me to every time write hat.
Okay,
That's all.
no problem.
Just a notation. Okay. You should not think that they are the true parameters or something like that. They are only the estimated ones. That's all I'm saying.
Okay, sir.
Okay. So now two. The second step. What is second step? Anybody recalls? I just wrote it.
Compute posterior.
Compute posterior. Okay. So now here is okay. So how do you compute the posterior? Anybody knows the formula? Here the distribution is a jointly continuous distribution, right? So anybody knows the formula for computing the conditional likelihood posterior? So what we have is this. From this, how will we compute this? That's the question. Again, I am skipping hats everywhere. Ideally, I should put a hat here. Okay, but I'm just skipping it. So what I know is the joint distribution. From that, how will I compute this particular conditional likelihood? That's all is my question. Any formula you know from?
The probability of y intersection x by probability.
Right, so it's not, yeah. So you are talking about conditioning of events. So we are talking about conditioning of random variables. So please revise the, but anyway, the formula looks very similar. You are right. It is this. Okay, everybody perhaps now will recognize the formula, but this is not the formula for conditioning on events because x is not an event. Okay, so x is the value the random variable set. This is about conditioning of random variables. This is described in section 3 of your Sheldon Ross book. Okay, so which I have asked you to revise some time back. So even if you are not revised, please go back and do it at least now. Okay. Nevertheless, the formula looks familiar, right? So this is, this looks very similar to conditioning over events. Okay. Now let's assume this formula is correct. Now if you have to compute this formula, this I know, but this I have to compute. How do I compute this marginal? This is called as marginal, right?
Integral over y.
So you have to do integral over y. So take a minute and try to do the integral over y. Whoever said integral. So this is correct. Whatever somebody said, it is correct. No doubt. Okay. But let's compute the integral with respect to y. Just take 2 minutes and do it. Maybe I need not convince you that integrals are difficult, right? Already you are complaining that you have lost touch with integrals. So should I assume that you are already convinced that integration is difficult in this case? or should I wait for 2 minutes?
Sir, there is no y term in the denominator, right? I think in that case it will be y into p of x.
Y into
P of x.
which one?
The
So where?
denominator.
Which denominator? Okay. This one?
Yeah.
Okay. So what's your observation?
Actually, in the previous step you mentioned like it is a function of x only. There is no y component, right?
Right. Which one? This one?
No. Actually, uh, one step behind, like p of x comma y by p of x.
Right. This one.
Yeah.
Are you talking about this?
Yeah, correct.
Okay.
So exactly we are doing the
Oh,
integral with the
okay.
denominator term, right?
Right. So this is the formula, right? So
Yeah.
this is called marginalizing, right?
Yeah. Okay, fine.
Since we have only samples and don't know the actual function, we won't be able
No.
to.
See again, please don't get confused with that. Always we are using mu hat. See, samples are over. After first step, there is no samples. We have this mu hat and sigma hat, and hence we have this distribution p hat. So
Okay.
from first step onwards, we are only talking about hats. That means approximations. That is fine. But still, so I'll put hat just to make sure all of you are in. Okay, so this is all hat. Okay. Okay. So there are no samples here. There is a there is some likelihood function which is given, which is p hat. Now it does not matter to you for step 2 whether it is obtained from some samples or whether it is obtained from some other process. You have this p hat. Now the question is how will you compute the corresponding posterior? That's all is your question. So is this clear?
Yes, sir. Got it.
Right. So Sophia, right?
Yes, sir.
So, so please understand that after step 1 there are no samples. You just have a joint likelihood. Now your question is how will you compute the marginal that is given by this integral, and then from these two how will you compute the posterior that's given by this formula, right? So the blue formula, right? Okay. So can you now rephrase your question? You are trying to say something. I interrupted you.
No, now it is clearer, but now I don't see why integral would be difficult. We would like, since we have p hat, we know that function and we should be able to integrate it, right?
Okay, I mean integrate and tell me, no?
Okay, because okay, difficult.
Okay, so see if you are very good at integration, even then what will happen is to compute the the constants, normalization constants, and so on and so forth, keeping track, and then dividing this by this. So go home and try this. That will take a lot of time. If you want to first compute, marginal, then do this division, and hence compute the posterior. All this will take time. Okay, so in fact, in many a case, you can be smart and do a lot of simplifications. Okay, so what I'm going to cover now is to implement such tricks where you can compute this posterior in a far more straightforward way in maybe less than 10 minutes or so, right? without going into details of integration and so on and so forth. Okay, so please focus your attention on what is coming. So here is what I am going to say. Now let us again start with the exact formula. The formula says I have my joint and I have to divide by marginal to obtain the posterior. Okay. Now the first comment I would like to make is, please observe that the denominator is not a function of y. Not a function of y. That means what? In terms of, and what is the random variable in this distribution? Is it y or x?
Y.
Y, right? So whatever is the formula for the likelihood, if I suppose write down the formula for the likelihood, right? There will be terms involving y. There will be terms involving perhaps x and y, both. Perhaps so there will be all these kind of terms, right? There will be terms involving only y. There will be terms involving x comma y. There will be only terms involving x. There will be constants, right? Out of all these four kinds of terms, only these two terms will be the terms which are important for this likelihood function, right? Because only these two involve y. Now given this function, in fact I can, so these two, what will they be? They will be like the normalization constant. Agreed? Everybody gets this point? What's the normalization constant? Okay, I don't know if you...
Sir, could you repeat that?
Right, I'll repeat. So I'm not sure if all of you are familiar with this terminology. So suppose I take this function. Which function do you know? Integral. So let's say e to the power of lambda x. Okay. So suppose somebody tells me that this is the function. This is my likelihood function x is proportional to this. Okay, where x is greater than 0, lambda is a parameter greater than 0. Okay, so what is the person saying? The person is saying he has a likelihood function which is proportional to this. Okay, now what do they mean by this? When somebody says this, what they mean is, see, can anybody recall for me what are the only two properties that a density function need to satisfy?
Integration should be 1.
Right, very good. And then the function should be positive, taking on positive values, right? Only two things. So any function which is non-negative and which integrates to 1 is a valid likelihood function, right? Now here in this case, somebody is giving you a function which is obviously non-negative. E to the power of anything is non-negative, right? Now so many times people just specify such parts which are functions of x and leave the rest of the part of the definition of the likelihood function. Why? You can just retrieve it by the condition that integral of p of x dx is 1. For example, in this case, let's find out what is the actual likelihood function. Okay. So if this is the proportionality, what should be the likelihood function? It should be some constant times e to the power of lambda x. Agreed? So now our goal is to find this constant c. So this is called as normalization constant. Okay. So let's find, for example, for this function, what is the normalization constant? How will you find? You will simply use this equation. Integral c lambda x dx should be 1. That will happen if and only if, what is the value of integral? First let's compute. So this is c integral lambda x dx should be 1, correct? But what is this? Anybody can tell me what is the integral of e to the power of lambda x? And what is x domain? X is 0 to infinity, right? So this is 0 to infinity. That's the limits. So what is this?
E power lambda x by lambda.
Yeah, how did you get that? Because maybe you will do change of variables. You will say lambda x, I'll call it as x. then what will happen? This will be 0 times lambda times 0, which is 0, and lambda times infinity, which is infinity. Then you will get e to the power of x d of, you have to write, so this is say x bar, then this is x bar, right? Now you have to write dx as dx bar, that's simple. So dx is equal to dx bar, right? So I'll get dx bar by lambda, right? Okay, now what is this? This is equal to, at infinity, what is it? This is turning out to be something. So let's say minus. Should we say minus? Yeah, I think let's say minus. See, now you are seeing how people can play with likelihood functions, right? So suppose somebody started with this, what will he get? He'll get this. But what is this integral value? Let's do this just for, what is the value of this integral?
Infinity. E power x only, but if we apply infinity, right? Infinity.
You will get infinity, right? So infinity minus 1, which is infinity, right? So what is the value of this integral? Infinity. So there is no c value for which c into infinity will be 1. So you will say this can never be a valid likelihood function, okay? Because it's basically area under the curve is infinity. But let's start with this. Suppose I say this is the, let's put a minus sign. Then suppose somebody claims that this is, how will you verify? You will basically, or find the constant. In that case there will be a minus sign, so you will say minus is this, say, then 0 to minus infinity, that's what it will be, and this will be minus, right? So this will be minus of, okay. So now if you apply limits, what will it be? So let's first compute. So this will be minus e to the power of x bar by lambda. That's going to be the integral between the limits 0 to infinity, right? But what is this? What is e to the power of, 0 to minus infinity? What is e to the power minus infinity? 0. So I have 0 minus of minus e to the power of 0, which is 1 by lambda, right? So what is this equal to? 1 by lambda.
1 by lambda.
So that's finite, right? So good. So that means this function can be a valid likelihood function. So what is the corresponding normalization constant? C into 1 by lambda should be 1. That is if and only if C equal to lambda. Okay. So what is this likelihood function? Original likelihood function? It should be this, lambda times e to the power of minus lambda. Now anybody knows the name of this likelihood? Name of this distribution, please. Nobody saw this earlier?
Poisson.
Poisson.
Exponential
No?
distribution.
Exponential, very good. Poisson also looks similar, but Poisson is discrete. We are now here talking about integrals. No, it's a continuous. So exponential distribution, very good. Okay, so now you understand what's the normalization constant, right? What is normalization constant? Basically terms which are not having x. That's the definition of normalization constant, the random variable. Okay, so in this case, what are the terms that don't have y? The terms which have x and the constants, right? All of them are normalization constants. Everybody agrees?
Yes, sir.
Because given a small x value, whatever function of small x is, that's a fixed number. So that's the normalization constant for the distribution. So your focus always should be to actually get the form of the likelihood function in terms of y. The rest all can be got by integration later on. Is that clear? So this trick is used many times by people. People only try to find out what is the form of this function, likelihood function, in terms of the random variable values. Why? That's enough, because the other parts, which is basically the normalization constant, can always be found out later by integration. Or if you are familiar, if it turns out to be a form which is known, like for example exponential, Gaussian, and so on, then everybody knows the normalization constants, right? So for two reasons, people postpone this idea of computing normalization constant at every step, because if you keep computing normalization constants, you have to keep doing integrations, and finally what may happen is when you are dividing or multiplying in your formula, these normalization constants may get cancelled out, and it may be very painstaking for you to keep the bookkeeping, do the bookkeeping and keep track of whatever got cancelled and whatever didn't cancel and carry on and so forth, right? So what people cleverly do many a time, please remember this, is they avoid computing normalization constants in the first go. They will only focus on what is the form of the likelihood function, that is what are the terms that involve the value of the random variable. That's all they'll be computing. And once they get a simplified form for that, then if that form seems to be familiar, then they don't need to do any integration, because already people would have computed such normalization constant. And if it turns out to be a new distribution form, you can now do one integration, that will be enough, instead of doing many integrations wherever normalization constants came in your formula. So is this philosophy clear to all of you?
Yes, sir.
Of postponing.
Yeah.
So basically you are being lazy
Yes,
to
sir.
compute the normalization constants. Okay, now let's be lazy again. So if we have to be lazy, one thing is clear, this denominator can be ignored completely, right? You don't even need to compute it at the current level. Secondly, what about the numerator? Numerator also, it has two kinds of terms. Again it has four kinds of terms, right? Only terms containing y, xy, x and constant. So suppose I write down only those terms which involve y, then I'll be done, right? So essentially what should I do to compute posterior? I don't need to compute the marginal over x. I don't even need the entire joint. I just need those terms in the joint which involve y. That's all I'm interested in. So is this clear to everybody?
Yes, sir.
Why are we
Okay.
ignoring the term with y?
Why are we
Ignoring the terms including x and y.
uh, x and y? We are not ignoring. Terms including y includes the terms including x and y. We are not excluding them. They should not be excluded. Any other clarifications, please? Okay, so if the philosophy is clear, let's put this philosophy into action. So for this case, let's try to write down cleverly what is the posterior, right? Posterior will be proportional to the joint, and even in joint it will be proportional only to terms containing y or y. So let's write down the term. So first of all, we can ignore the normalization constant. Secondly, there is e to the power of minus half x minus, so x, what plays the role of x? X and y play the role of x. Then sigma inverse, then x, sorry, this is, there is mu also, right? X minus, so the usual formula is x minus mu transpose sigma inverse x minus mu, but here what is playing the role of x? X comma y, right? So I am having here so I should actually write, so here what plays the role of x? X comma y. Okay, now because for my convenience, what I will do is I'll also split mu into two parts. The first part of n size I'll call it mu1, the second part I'll call it mu2. Is that clear? The notation is clear? So then this will be x minus mu1 transpose y minus mu2, that's the vector, sigma inverse x minus mu1 y minus mu2. So what is mu1 mu2? I simply broke mu into two parts, the x part and the y part. So is that clear to everybody, the notation? Okay, so this is correct, right? So this is correct because I'm only writing proportionality. Please note, I'm writing proportionality, I'm not writing equal to. right? So whenever you are writing proportionality, you have to remember two things. You should not write things which are not dependent on the value of the random variable, that is in this case y. Secondly, you should not forget any term that involves the value of the random variable, that is y. Okay, so both you have to do. If you forget some term which involves y, then your answer will be wrong. That's worse. Okay, and if you forget some term, if you by mistake include a term which is a constant or not dependent on y, that's okay. It will not, the answer at least will not be wrong. It will get only unnecessarily cumbersome. Okay, but if you want to
Sir,
be yeah
one quick question. So
yeah yeah
why we are saying y as a random variable y and not x?
no, x is given, no, x is observed. So in conditioning of random variables, the random variable x is a random variable that has been observed. That's what given means, no?
Okay.
What does given mean? It means
Mm-hmm.
x random variable has been observed to be small x. That's the meaning.
Okay. Yeah.
Okay, so in after observing that the x random variable has taken small x value, now your question is what is the distribution of y? That's what y given x distribution answers. Okay,
Yes.
is this clear?
Yes.
So imagine this. See, there is some random experiment. Okay, a big random experiment going on. Now, from this random experiment, you have various sensors. So, think about a random experiment as your usual lab experiment, right? And what are random variables? They are like readings of sensors. The random.
So your
Yeah.
your voice was not audible, sir, for few seconds.
Okay. So I'm repeating. So think about a random experiment, which is nothing but a abstraction of your lab experiment. Okay. Now, in a lab experiment, you will have various sensors and meters and their readings, right? So these are like your random variables, right? So the abstraction for them is random variables. Okay. Now, if the physical process is known, that's like knowing the underlying distribution of these readings. That means the readings, the values of these random variables. Okay, the next point is that suppose you ask this question, what is the distribution of some particular sensor reading, that is say y, which is called y. Okay, now that question is different from asking the question, if my other reading of meter x is something, then what is the distribution of this meter reading? That's, these two are different, right? So that's what is the difference between the marginal of y and y given x. Okay, so is it now clear to you why x is not a random variable in y given x?
Yes, sir.
Okay, so shall I proceed with this derivation? Okay.
Yes, sir.
Okay, so now let's ask both these questions. What are the terms which I ignored at this step? Can anybody tell me?
Root over 2 pi sigma square.
All those 2 pi, those determinant, those terms I ignored. I can safely ignore them because they are not a function of y. Okay, then I did not ignore any term in y for sure. Okay, now even in this thing there are many terms which are only a function of x. Okay, so let's separate those terms and write things clearly. Okay, now what are the terms which involve only x? For example, there will be a term which they take this vector and multiplies a part of this matrix and with this, that will be a term which only involves x, right? Okay, so if I have to nicely know these terms, I should also break, like I broke the mu vector into two parts. How many parts should I break sigma inverse? Suppose I call sigma inverse as lambda matrix. The name for lambda matrix is precision matrix. What is the name for sigma matrix? Covariance, right? So the inverse of covariance is called precision. This is just a terminology. Okay. Now my question to you is, because x was split as x and y, I split mu as mu1 and mu2, two parts. But now there is this quadratic term, this multiplied by this multiplied by this. Because of this, what should I split capital lambda as? Should I split it as two parts or four parts or
Four parts.
four, right? That's very clear. Okay, so let's do that. So let's split mu minus mu2, and the first part let me call as lambda 1 1, lambda 1 2, lambda 2 1, lambda 2 2, and then this is okay. Just to make sure if all of you are on same page, let me ask some questions. What is the dimensionality of lambda 1 1? What will be the dimensionality of lambda 1 1? Will it be a number? Will it be a square matrix? Will it be a rectangular matrix? Whoever answered four parts should be able to answer this at least. Hello?
Square matrix.
Yeah, so it's a square matrix. Is everybody able to hear? Am
Yes,
I
sir.
audible?
Yes, sir. Now you're audible.
Okay. Okay. So this is so everybody agrees that this is a square matrix of size n.
Yes, sir.
It will
Okay.
contain only the x terms.
Yeah, basically it will contain terms corresponding to x, not x, right? It is the covariance, part of the precision matrix which multiplies the x terms. That's how we should say, right?
Yep, covariance between the x dimensions.
Not covariance. It is actually the part in covariance inverse. So covariance inverse, it will not be these. You are understanding, right? See, covariance also can be split into four parts: sigma 1 1, sigma 1 2, sigma 2 1, sigma 2 2. But sigma inverse will be what? Sigma 1 1, sigma 1 2, sigma 2 1, sigma 2 2 whole inverse. Please understand that this is not equal to this. Okay, this is not. Hello.
Yes, sir.
Okay, so I'm not talking about this. I'm talking about this term. Okay. So in general, lambda 1 1 may involve all these terms. Okay, don't think that lambda 1 1 will be function of only sigma 1 1. No. So whoever said it will contain covariance of x terms, do you now agree that it need not contain covariance of x terms? It can contain xy terms also.
Yes.
But we are only taking that submatrix of size n by n. That's all. Okay, is that clear?
Yes, sir.
Okay. So what will be the size of lambda 1 2? Hello. Hello.
Yes, sir.
Same
I
is
think
it?
it
No.
is again. Yeah, same.
No, no, no. How will it
N
be
cross
same?
1.
Yeah, it is n cross 1. It's a row. It's a column vector. Okay. See, it's like this is a block of square, then the corresponding fellow should be a thin fellow, no? How can it be a square? And this will be a thin like this will be a dot, this is a number, right? That's how this matrix is. So just to finish, what is the dimensionality of this?
1 cross n.
1 cross n. In fact, can anybody tell me a relationship between 2 1 1 and 1 2? These two matrices, there is a relationship. Very good. So this is transpose of this. Why? Why?
Symmetry.
Very good. The covariance matrix is a symmetric matrix. So precision matrix also will be a symmetric matrix. So because it is a symmetric matrix, this will be true. Okay. Okay. Now, what about this? What is the dimensionality of lambda 2 2?
1 cross 1.
1 cross 1. That's all. Okay. So now okay, this is just for testing your understanding. Okay. Now let's carry on. So from this, what should I do? I should ignore terms involving x. So let's start. Now this term will multiply this and multiply this. That will give you a square term in y. Everybody agrees? That's how metric multiplication is done, right? This
Yes, sir.
multiplies this and this, that gives the square term, and this is the only square term. So let's first write down the square term. So it's minus
Again.
y. Yeah, hello, hello, hello.
Yes, sir, you are audible.
Yes,
Okay.
sir.
Okay, now this is the square term involving y. Now there is another term which involves y, which is what? The term that involves x and y both, right? What is that term? So maybe this multiplies this and then you multiply this, right? And then there is the other term, this multiplies this and then that multiplies this, but both these terms are same because of symmetry, right? So I'll get 2 times. So if I take half common, I'll get, so let me change the pen again. So I'll basically get minus or plus, right? Plus 2 times y minus mu 2 times lambda 2 1 times x minus mu 1, right? Okay, so everybody is clear till here? So it's like a square plus 2ab, correct? Yes, no? If you have any doubt, you can ask. So is it like becoming too much or what is the problem? Hello?
So why did we split that into 4 parts? I did not understand.
You are seeing, right, how matrix multiplying is carried out. See, if we did not split, then also this is how multiplication will happen, right? This will multiply this submatrix and that will multiply this, right?
Okay, got it. Because that
Okay,
y
I'm
part
just
is
naming.
one-dimensional and
Yeah,
x
yeah,
part has n. Okay.
right? I mean, I'm just naming them conveniently, that's all.
Hmm.
Even if you don't name them, this is how multiplication will happen. But when you have block, vectors, it is easy to, so block vector or block matrix multiplication will look similar to matrix vector multiplication. Only thing is you have to keep the transposes and all properly while multiplying, right? So any questions? Is this clear? Shall I go ahead? Okay, so what is the term that only involves x square? It is this term, multiplied by this, and that gets multiplied by this, right? And that we don't need to account for, right? We can just ignore it. Okay, so this is all the. Okay, now we have done. So what stage have we reached? We have reached the stage which we imagined. We wanted to write the likelihood function form for the posterior involving only the terms that are having y, right? Now in this, terms involving y are only there, right? Still you can remove the terms which don't involve y. For example, this, you can still expand the brackets and say this into this into this, that does not involve y. All those things you can do, but let's stop here and then ask the question, do you guys recognize this form of this function? So this is a quadratic function. You have e to the power of minus quadratic. Now that's a familiar form, right? That's the form of Gaussian function, right? So it looks like whatever is this distribution, it's again a Gaussian distribution because it looks like e to the power of some quadratic. So if it's a Gaussian distribution, what is the only thing to be remaining? The only thing remaining is find the mean and variance of this posterior. Now, when can you find the mean and covariance of the posterior? If you write the likelihood function in the standard form of Gaussian distribution, Gaussian likelihood, then you can just read out what is the mean and the variance, right? So that's what we'll try to do now.
Sir, it means that for a given x, y is distributed basis the
Very,
Gaussian distribution.
very good, very good. So what is happening is something beautiful that is happening. What we assumed previously is x comma y is jointly distributed as Gaussian, but now what's happening is even at a given value of x, suppose somebody told you x value is something, even then the distribution over y itself is Gaussian. That's what is happening. Right? Now that is clear from the form of this likelihood function. Now the only thing we are remaining to be done is to read out the values of mean and variance of that distribution of y given x, right? And if I have to do that, I have to write this in standard form. I should write it like e to the power of minus y minus mu square by 2 sigma square, something like that. I have to write it, right? So let me write it and then convince you why that is correct. Okay, so this is proportional to, so this is proportional to, so e to the power of minus y minus y2. Okay, so let me first match, okay, y minus y2 minus, okay, plus,
Sir, it's mu2 or y2, sir?
what is it?
Y minus y2 you said.
Sorry, y minus mu2. So I'm just writing it, y minus mu2 plus 2 inverse lambda 2 1 x mu 1 um, square, okay, by, so I should square into lambda to 2, just a minute, right, Right. So this, suppose I say this. Okay. Now let's see if all of you will agree with me or not. Okay. Now, so first of all, let us compare the quadratic term in y. Right. So sometimes, okay. So the quadratic term in y, that I should get this, right? So let's see. So this square into this. So is the quadratic term matching at least? Yes or no?
Yes, sir.
Okay.
Yes.
So let's ask the other question. Linear term in y. If that is matching or not. Okay. So let's ask that question. Okay. So what is the linear term? This is the linear term in the original. And what's the linear term here? So if I expand this quadratic, what will I get? That's when I'll know the linear term. So that will be 2 times y minus y2 into lambda 2 inverse lambda 2 1 minus this, right? Everybody agrees with this? That's the only linear term, right?
Yes, sir.
So that into lambda 2, right? This lambda 2. Okay. So this and this will get cancelled. Why? Because they are numbers. Lambda 2 is a number, remember. Right? So am I getting this blue term is matching or not?
Yes, sir.
Yes, sir.
That's all. Now we should match only terms in y, right? The term in x I can ignore. Only involving x I can ignore because I'm only talking about proportionality.
Yes, sir.
That's all. So there comes the answer. So this is basically, so what should this distribution be? So instead of calling this as lambda 2, let me call this as by. So instead of writing as into lambda 2, it's a number, right? So let me say by lambda 2 inverse. Okay. Now can you read out what is the mean of this distribution? So what is P of y given x? One thing is clear, it's a normal distribution. This is the notation we will use. But what will be the mean of y given x? Anybody? So let me call this sigma square 1 given 2. So what will be mean of y,
Mu 2.
y mu 2 given 1, 2 given 1, sorry. What will be mu of 2 given 1? Can you read out from this earlier expression of likelihood? From this blue expression, read out the mean of y given x. That's all I'm saying.
Mu 2.
Anybody? No, wrong. Is it only mu 2? See, what should you match this with? We should match this with this expression, no? E to the power of minus half y minus mu 21 square by sigma 21 square. So what should be mu 21? Very good. That's all, right? So this is just a matter of reading of things, comparing terms, right? So 21 x minus mu 1. So this entire thing is the mean. The mean is a function of x, of course, right? For different x's, you get different posterior distributions, right? Suppose x is the observable climate condition, y is rainfall, amount of rainfall. Then the distribution of rainfall should depend on the climate condition, no? That's all we are saying. The mean of the rainfall is a function of x. It depends on the climate condition. Good. So that's not worrying. It's a function of x is good. It's welcome. Okay. It should not be a function of y. Your parameter should not involve y. That's what you should be careful. Because y is the value of the random variable. Right. Okay. So please be clear about these three things. So what is the value of sigma 2 given 1 square? Anybody?
It's lambda 2 inverse.
Inverse. That's all. No square root, right? Because I'm only talking about square.
Yes.
Okay. 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 So that's all. Okay, so we are done with the second step, right? What is the second step? Computing posterior. And I not only computed posterior's form, it's a normal distribution, but I also told you what are the parameters of the corresponding likelihood, posterior likelihood. So we are done with step 2. So what is step 3? Anybody recalls in generative modeling?
Mean of this posterior.
Compute the mean. So who will tell me the mean? It's already written, right? So what is your g of x function? Just it is basically mu2. Again, let me put hats so that so all these are hat versions, not the. I ignored hat till now. That's all. X minus mu1 hat. So that's your final answer. Okay. So if anybody asks you to do generative modeling, these are the 3 steps you have to do. Okay. One is you actually model the joint. Second, you estimate in the first step itself, you estimate the parameters of the joint. So after the first step, you have a joint likelihood that approximates your underlying distribution. Then in the second step, you compute the posterior that looks something like this. Typically, what will happen is if you start with nice models, the posterior will also be, how is the posterior changing with x? The form of the function is not changing, no? Only the parameters are changing. So if you start with, nice models, this is what will happen. Otherwise, you can imagine nasty cases where for some x's it is say normal distribution, for some other x's it is chi-square distribution, or some other x's it is exponential distribution. So I mean, you can't say, right? So in a general model, anything could happen, right? But fortunately, if you start with nice models for the joint, the posterior distribution form will remain the same for every x. And at each x, how will they differ? Only differ in the parameters. So the parameters will be function of x. And interestingly, in this case, it is the variance is not a function of x. Interestingly or non-interestingly, whatever you want to say, this turned out to be not a function of x. So it would have been more interesting if this also was a function of x. But here it is not a function of x. That's what your original generative model turned out to be. Okay. Now, so is this clear till now? Okay.
Yes, sir.
So if this is clear, I'll now start giving many comments. Okay, comments which will make things clear. Okay. Now sometimes people write the same expression in terms of sigmas. So it so happens that this somebody already computed this in terms of lambda 1 1, lambda 1 2, lambda 2 1, and lambda 2 2. Okay, the formula is called Schur complement formula. So what the formula does is it gives values for these lambdas in terms of these matrices sigmas, and that is useful, right? So somebody was telling that lambda 1 1 is nothing but inverse of covariances of the x part. No, that won't be the case. Okay, so it is a more complicated formula. Now what is that complicated formula? If all of that you want to know, please go home and refer what is called as Schur complement formula. Okay, but if I apply that so-called formula and rewrite this is what will happen. This will what will be the expression for sigma. So this will be sigma hat 2 1 sigma 1 1 hat inverse x minus mu 1 hat. So if somebody did not understand, don't worry. I'm just saying this is same as this. This is equal to this. Why? It is Schur complement formula, whatever that is. Okay. So let's not worry too much about that formula. So Schur complement formula. From that, this comes. Okay. Now let's start understanding this formula. That is more important for us. Okay. Now, suppose I call this entire thing as x bar. Okay. And I call so g hat of x minus mu2 as some g bar of x. Okay. Then how is this formula looking like? This is just a notation, but that notation has a meaning, so I'll tell you. So g bar of x is equal to this into x bar. That's what is the equation, right? Okay. Now let's understand what is x bar meaning. Now what is mu1 hat? It is the mean of the input vectors. What is sigma 11? It is the covariance of the input vectors, correct? Now, if I do such a computation and compute x bar and ask what will be the mean of x bar, right? So did you understand my question? The data is x1 to xm. So instead, if I compute x1 bar to xm bar, what will be the mean of this average of this?
Grand.
Eh?
0.
Very good. See, I just subtracted the mean, right? So what will happen if I add by, if I just take a summation of all these things, it will be summation. Sorry, this is summation, not covariance. So summation over I of xi bar minus mu1 hat by. So this is not by. So this is into sigma 1 inverse, right? So what will this be? Simply this will be, so this will be sigma I xi sorry x minus mu hat. So this is sigma xi bar minus m times mu1 hat. But what is sigma xi bar?
M times mu1 hat.
M times mu1 hat, that's all, right? So it will be 0, right? So what am I doing here? I am doing a mean subtraction, so I am making mean 0. And can anybody tell me what will be the variance of these terms, covariance of these? It will be identity because of this term. You can go home and check. Okay, so what am I doing here? I'm actually doing a mean 0 unit variance normalization. So this such things are called as normalization. Why are they? And it's a pre-processing step. You can consider this as a pre-processing step. Why? Because only given inputs values, not given the outputs, I can compute mu hat, mu hat 1. I can also compute sigma 1 hat. And with that itself, I can transform my inputs into x bar. Right? So you can consider this as a pre-processing step. So suppose somebody does this so-called zero mean unit variance pre-processing, then your inputs will be like x bar and your equation will look like this. Okay, and in terms of y, what are you doing? You are just mean subtracting. So it's not unit variance but zero mean normalization. So if outputs you normalize as zero mean and inputs you normalize as zero mean unit covariance, then your formula looks like this. That's all I'm saying. So this is this clear to everybody? Now I'll tell you what is good about this equation. So if this is clear, I'll tell you what is good about this equation. So till now it is fine. I'm just normalizing my outputs and inputs. That's all.
Sir, actually, should it be g bar of x bar?
This is g bar of x bar, correct? Yeah, that's true. Okay. Now what is good about this estimate? See, what is happening is, so this equation has a very nice simple interpretation. That's why we are doing all this normalization interpretation. So what is, let us give what is the interpretation. Okay, the interpretation is very satisfying. Now what is the meaning of sigma 21? It is the covariance of the outputs with the inputs, as simple as that. What is sigma 21? It is simply the covariance of the output with respect to the inputs, correct? Yes or no? So what we are saying is just take the normalized inputs, multiply it with the covariance of the inputs and the outputs, then whatever you get is the output, normalized version of the output, right? So that is a very satisfying explanation, right? So you're just, so if all my relations were linear, then this would exactly be my equation, right? So in case of non-probabilistic modeling, what was the model we used? W transpose X. Y is equal to W transpose X. Now what's playing the role of W here? So W is like, very good, that's all. Okay, so this is what is, and what is this? This is the covariance, the way output is correlated with input, right? So when the normalized vectors are being used, covariance is the same as correlations, right? So how is my output correlated with my input? That's all I'm asking, and that plays the role of W, right? So I'll take the value of input, I'll multiply it with the correlation, how is it correlated with the output, and that gives me the value of the normalized output. Okay, so this equation is very intuitive, right? Okay, so previously when we did linear regression, if you remember, what was the expression for the function, base optimal function? I'm not sure if you guys remember. It was something like this: y transpose, here y is different, y was the vector of all training outputs. It was yx, so in our notation it was something like this, I think. Transpose x transpose inverse into x. Okay, so this was what turned out to be in case of linear regression, if you guys remember, because W was estimated as xx transpose inverse x transpose y, right? So if this was the, was it x transpose or x into y? Let me just, so it was x into y, right? Okay, so this is with the transpose. Okay, so this is what we get. So in case of linear regression, what did we get? We modeled the base optimal as a linear function, but my parameters were estimated like this. Now in this case, we did not directly model the base optimal. What did we model? We modeled the joint distribution as a Gaussian distribution. Now, did any one of you imagine that if I model the joint as Gaussian, then the corresponding base optimal will turn out to be a linear function? Did anybody guess? Any one of you guess? No, right? I mean, did any one of you guess? I'm really asking this question.
No, sir.
Right?
No,
So
sir.
typically this is what will happen. In generative modeling, what you start with is an assumption on, it's an assumption at a very high level. You assume something on the joint distribution. Now what assumption on the joint distribution turns out to be what assumption in terms of the base optimal is many times very unclear. Okay, so generative modeling is is far more involved than non-probabilistic modeling. This is the reason, right? So why? Because the relationship in terms of the base optimal is not known. Even in this case of Gaussian, when things are so symmetrical and well known, the derivation took almost 1.5 hours for us, right? Imagine a situation, a new situation in which you use some, some modeling for the joint, and you want to know what it turns out, what form of the function it turns out to be in case of the base optimal, right? So guessing this is completely non-trivial, and in many cases you may not even get such a nice analytical expression for the form of the base optimal function. It could be only expressed in terms of some numerical solution maybe, right? So so that's the reason why generative modeling is very, very difficult and challenging, because you don't know what changes you have to make in your model to reflect as what changes in the corresponding base optimal. Is this point clear to everybody?
Yes, sir.
So the second thing I want you to observe is, nevertheless, in this case, what we actually showed is, if you start with the assumption of Gaussian on the joint, then it is same as assuming the base optimal is a linear function, right? So at least the base optimal form turns out to be a linear function. So this is the corresponding generative model for linear regression. Okay, so you may call whatever we did now as generative linear regression. That is one name we can use for the for whatever we have done now. Okay, generative linear regression. Okay, why the name linear regression? Because the form of the base optimal turns out again to be linear. Okay, so the blue form which is on the screen, right? Okay, but don't be mistaken, the values of the parameters are quite different, right? So this is the covariance, and here this is not the covariance, right? So the values, so this particular fellow is not the covariance, right? So this fellow in gray. So the values of the actual parameters of the linear function, which are estimated according to the generative model and the linear regression model, could be very different. Okay, but the form of the function happens to be the same, which is linear. Okay, so similarly, many a time we can talk about corresponding models. So what is the corresponding generative model for this non-probabilistic model, or what is the corresponding non-probabilistic model for this generative model? People keep asking such questions. Okay, now this exercise should have given you some idea of how the answers will look like. Okay, then the next comment I want to make is the following. So this is a very, so I'll stop with this comment, but let me see. Till now I told you one disadvantage of demerit or con.
Sir, I have a question.
Yeah, please.
So now we know the form and shape of the base optimal in this for a linear equation when we consider the distribution as multivariate version.
Right.
Now, if how do we solve a problem where we are given a data set and we just solve for this equation, like we calculate the covariance between input and output,
That's all.
and then
That's all.
standardize the norm inputs and outputs and just equate
Right.
it.
Yes, that's all. Just when a new x bar is given, when a new x is given, compute the x bar using this normalization formula, right? When a new x is given, compute this normalization, get x bar, then just multiply with covariance of the outputs and inputs, and that will be, and add it with the mean of the outputs. That will give you the prediction value. So as simple as that.
Okay.
So this is basically the entire formula. We looked at the formula in a particular way. That's all. We gave an interpretation. That's all. Otherwise this just looks like a formula, right? So we gave just gave an interpretation for this formula as this formula. That's all. So
So
any
it
other
means
question?
from the training set we are learning the value of covariance. That's it.
Exactly. That's
Okay.
it. That's it. That's it.
Okay.
See, here you are in linear regression, you are not learning covariance, but you are So these are actually like correlations. If you can, imagine, these are not like correlations. These are not like covariances. These are like correlations. So this term very much looks like a correlation, right? X into X, right? So and this actually looks like correlation between outputs and inputs, isn't it? X is being multiplied by Y.
Yes, sir.
Right? So this is playing the role of this. This is playing the role of this. So apart from some normalizations, actually linear regression also has the same interpretation. It is also normalizing X. So you can also call this as X bar. So this gray colored, oh sorry, I should use more colors. This green
What you are
colored.
writing, I'm not able to see. Maybe I'm the
So
only one.
okay, no. Now you are able to see. I didn't change the color. That's all. Now you are able to see green.
Okay, okay.
Should I call you Dikshitulu or what is your name is very big?
Tittakavi.
Dittakavi is your first name?
Yeah, surname.
Yeah, but what is your first? How do you call you?
Bhat.
Bhat.
Yeah.
Okay. So Bhat, this green color, are you able to see on the screen?
Not really.
Oh, okay. Is nobody able to see my screen?
We are able to see, sir.
Okay,
Yes,
so
sir.
but you have a problem.
Okay, no problem. Continue.
Okay. Okay. So if you guys are seeing the correspondence, this green color also is like normalizing the inputs, and that's the version of it here is this. So this is also like normalizing. The only difference is that this the first normalization is using zero mean unit variance normalization, whereas the second green fellow, it's using correlations instead of covariances for normalization, and it's not doing mean subtraction. So apart from that, you can also call it as normalization, right? And secondly, if this is the, so let me use an pink. So this term, oh god, this is horrible. So let me use some pink is fine, or oh god. So this, okay, this pink is okay, I think, right? So the pink fellow was what was capturing the relationship between outputs and inputs. That was done by a covariance term in case of the probabilistic model. But in case of the non-probabilistic model, what's playing the role of interactions between y and x? It is y into x kind of terms. So it's basically like correlations again, right? Again, there's no mean subtraction term. So this, let me use another color, maybe orange. So the orange term is completely missing in the non-probabilistic case. In the non-probabilistic case, there is no mean subtraction being done for the outputs as well as inputs, and hence all correlations are being replaced by covariations are being replaced by correlations. So apart from mean subtraction, actually both these formulas are the same. That's what happens to be the answer. So is this connection, close connection between probabilistic, this generative model and linear regression very clear to all of you?
Yes, sir. Sir, I have a follow-up question.
Yeah, sure.
Maybe you have not introduced the term, but I'm just curious to relate. So, in the probabilistic modeling as well as non-probabilistic modeling, there is a direct equation that we are getting on which if you can consider the weights as well as the covariance matrix, it's we are directly generating from the training data. Now, where does this gradient descent kind of algorithm fits in? Where the purpose of those algorithms is also to tune weights. So where?
Yeah. Okay. So to derive this equation, oh god, this is a bad highlighter. Let me just, okay, this one. Okay, this is also bad. I'm just picking a better highlighter. Just a minute. Which one is not used? Okay, yellow. Okay. So this fellow. So look at the yellow term. Right? So how did you compute the W? Do you remember how did you do this formula? By putting gradient equal to 0. Do you remember?
Yes.
Right. Now, in this case, we were lucky that putting gradient equal to 0 was very easy, and it turned out to, there was a unique solution if this matrix was invertible and so on and so forth. Right. But in a general case, that solving gradient equal to 0, that equation, that's an equation, right? Grad of the function equal to 0. That may be a non-trivial set of equations to be solved. In this case, it turned out to be a unique solution. But in a general case, that set of equations need not have an analytical solution. You may have to solve that using a numerical algorithm, right? So in those cases, that's where exactly gradient descent is used. So when you want to put gradient to 0 and you can't have an analytical solution, one way of numerically putting gradient to 0 is gradient descent. You will start with an iterate, then you will keep, moving the iterates, going in the opposite direction of gradient. All this you will do to put the gradient value to be 0. Finally, you will reach a point where gradient is 0, hopefully.
Yes.
So here also you are doing the same, no? This is a point where, point W, where gradient is 0. The yellow one, that's also a point where gradient is 0, right? But in this case, fortunately, gradient 0 point had a expression, easy expression like that. But in a general case, like for example, logistic regression, I already introduced logistic regression to you, right? There, try to put gradient 0. You can't solve the corresponding set of equations you get. There's no analytical solution for it. You have to come up with a numerical algorithm to solve it. And there, people use gradient descent to find such a point where gradient is 0. So is that clear?
Yes, sir.
So gradient is a gradient descent which you learn in optimization or in other ML courses. The place where it goes is in parameter estimation, basically, to solve the maximum likelihood estimation problem or to solve the ERM problem. These are the places where you will use gradient descent. Now, fortunately, we took very special cases where solving the MLE problem or solving the ERM problem had closed form solutions. So we did not bother about introducing gradient descent. Okay. Now, if you guys remember, and the other reason is, see, people typically don't know optimization much. So I tend to skip all details of optimization in my ML courses, and that's a bad thing to do. I know ML is full of optimization. In fact, we showed in the beginning of the course that the basic ML problem itself is a stochastic optimization problem. So not talking about optimization problems details in a ML course is criminal, I know, but let me be pardoned for just for sake of simplifying matters to match background of students. Okay. So if the background of students was such that they already know optimization, then I would use a lot more of optimization terms and take problems where you know these algorithms are used heavily and so on and so forth. But to some extent we will do it. For example, we gave details of perceptron algorithm. Later on, I hope to cover some details of stochastic gradient descent. That's another alternative to ERM. So if you remember, ERM was one approximation for solving the supervised learning problem. There's another way to, entirely different way to solve the approximate the supervised learning problem, and that's using the notion of stochastic gradient descent. Okay, so that I hope to cover because it is related to, that's what is used heavily in deep learning. So because it's related to neural networks and deep learning, and in general also very useful, maybe I'll try to cover if time permits. Okay. So are you able to hear me?
Yes, sir.
Okay, so this is about the place of gradient descent. Did I answer your question?
Yes, sir.
Okay. So any other doubts, please? Okay, so we'll do one thing. Instead of keeping on giving comments, I'll take a break. Okay, let's meet at 4:20 exactly and resume the proceedings. So instead of giving more and more comments, what I'll do is I'll start with classification. So now we did generative modeling for regression. In the next part of the lecture, we'll do generative modeling for classification. Okay. And we'll start with a very simple model like in this case and see how the corresponding classifiers look like. Okay. Okay. So let's meet after the break.
Hi, Abhiram. Hey, Anurag.
Hello. Are you able to hear me?
Yes, sir, right now.
Okay. I think my mic was muted. So are you able to see my screen?
Sir.
Hello?
Yes, sir, we are able to.
Okay. Okay. So now let's try to solve the problem of classification using generative modeling ideas. Okay. And let's focus on the special case where the inputs are in n dimension and the outputs are only 2. So it's a binary classification problem. Okay, so let's just call the classes as -1 1. These are not the numbers -1 1. Just let's call the classes as -1 and 1. Okay, so or instead of -1 and 1, let's call it as 1 and 2. Okay. So for this case, let's try to see how to do generative classification, generative modeling. Okay. So what is the first step in generative modeling? Try to model the unknown joint distribution, right? Now, unfortunately, in this case, as somebody pointed out earlier, there is no one model which we know of, which outputs, some real numbers followed by a discrete value, right? So that's the problem in this case. So there's no clear model which we will employ for modeling the joint, right? Because none of the models which we know of either output real numbers or output discrete values, but this one requires to output both kind of values simultaneously, right? So that is not possible with the models which we have learned till now, right? Now what's the alternative? The alternative is to do modeling of the joint indirectly. So let's see what does indirectly means. So let's first understand what are all the distributions related to this joint. There are 4 distributions related to this joint, right? One is, there are 2 marginals, the marginal over x, marginal over y. Similarly, there are 2 conditionals, the posterior and the conditional, class conditional, right? Now, if you, in these 4, if you model this, it's what is called as, what is so if you model this, what is it called as? It's called as discriminative modeling. Okay, so definitely this is to be untouched when you are talking about generative modeling. So what are the options left if you have to model a joint? You have to model some of these 3 likelihoods. That's the only possibility, right? Now obviously if you just model these 2, you can never get the joint, because from marginals you can never compute the joint distribution, right? That's, I can show you multiple joint distributions which have the same marginal distribution, right? So that's not a correct choice, right? But these 2, suppose I model these 2, then it is fine, right? Why? Because if I model these 2, then I can always compute the posterior using a formula. So does anybody know a formula to compute the posterior from expressions of class conditional and the marginal over y?
Vidya, close the door.
Base form, base.
That's called the Bayes rule, right? Very good. So that's the Bayes rule, which gives me this, right, by p of x, but p of x is simply integral or whatever, a summation, whichever is the, so in this case it is integral, right, or it's summation, it's a summation. Okay, let's write summation over all y, this one, right? Okay, so what is this called? This is the Bayes rule, right? This is the Bayes rule for random variables, not for events. Okay, so this looks very similar to the Bayes rule for events, but nevertheless it holds for conditioning of random variables also. Okay, so what did we recall till now? What we just said is, suppose you model the class conditional likelihoods, and suppose you model the likelihood of the outputs, the marginal of the output, then you can compute, of course, the other marginal, that is what is this. So this is not in yellow, sorry. So this you can always compute. This is nothing but p of x, right? And from all of these you can also compute this, right? And this is what is needed in the second step, right? Okay, so so how, what is the idea? The idea is to model the class conditionals and the marginal over y. Okay, so now let's ask this question: do you know of any model that can model the marginal over the outputs in this case of binary classification? Which model will you use to model p star y?
Non-probabilistic.
No, obviously it's a probabilistic model because we are trying to model a likelihood. Very good, Bernoulli, right? So Bernoulli is a distribution which takes on two discrete values, and that's what y is also taking on, right? It's taking on two discrete values. So a suitable choice for such a situation is Bernoulli. By the way, don't think that I'm saying Bernoulli is the only choice for distribution. Actually, if classes are only two, perhaps this is the only choice. But anyway, what I'm just trying to say is, out of the four models which we are considering, which we know of, which is the one which gives you a right match for the kind of outputs the random variable takes, the kind of values the random variable takes. Okay. Okay. So since y takes two discrete values, the obvious model for the distribution is Bernoulli distribution. Okay. Now, what about the class conditional? First of all, how many distributions are there here to be modeled? If you want to model the class conditionals, how many distributions should be modeled? Here there is only one distribution, right? The marginal of y, that's just one distribution. So one distribution is being modeled by Bernoulli's. Okay, so out of all for Bernoulli's, I'll find one Bernoulli which is the suitable candidate from the data. Okay. Now what about class conditionals? How many distributions are there first of all here? Two, right? Very good. So there is one distribution for every y. So I have to model p star of x given 1. I should also model p star of x given 2 when the class is 2, right? So is this point clear? Yes, no?
Yes, sir.
Okay. So now which model will you use for either case? Mind you, x is a n-dimensional real number. So which model will you use for these likelihoods?
Multivariate Gaussian.
Very good. That's all, right? So now you got the, I think now it is clear how you play this game of modeling at the simple stage. Okay. Okay. So we are done with the modeling. So what are we considering? We are considering a joint model where the class conditionals are given by Gaussian and the marginal over y, okay, is modeled by Bernoulli. Okay. Now people also give a name for P star y. It's called the prior distribution, prior likelihood. Okay. Why the name prior? Because this is called posterior. This is, why was this called posterior? Because it's the posterior likelihood of outputs after, posterior to what? After seeing the input, right? And this is before seeing the input. So it's called prior. So is the not a terminology clear?
Sir, one quick question, sir.
Right.
Yeah, so I'm a little confused here because with respect to X we say it's a Gaussian distribution, and with
Right.
respect to Y we are saying Bernoulli. But
Correct.
in case of when we were doing non-probabilistic, we also spoke about IID, right, where it should be identical distribution. Does it has
Okay.
something to do with that? Because in that case these two are not identical distributions, right?
Okay. So now I'll tell you. No, identical distribution is not a property of distributions. It's a property of samples. Okay. Please note this.
Okay.
IID is a notion related to samples, not related to distributions. Okay. So you say two samples are independent and identically distributed if both of those have the same distribution. Okay. Now, what are we saying that which are the artifacts that are IID? It is the training examples, right? So what are we saying is we are saying that suppose somebody did a random experiment and collected data and he got this data. XM2. Okay. Now somebody else repeated the same kind of experiment n times. They would have gotten some other data like this, right? Xm dash to ym dash. Similarly, if another person repeated, he will collected another set of m samples, x dash dash maybe, right? Now, whatever that is, now if I ask you, can you tell me what is the distribution of all the first samples collected by each person? That will again be p star x comma y, right? And
Yes.
similarly, what is the distribution of all the mth samples collected by all? That will again be p star x comma y, right? Okay. Now, IID means this random variable which corresponds to the first sample and this random variable which corresponds to the last sample. These are identically distributed. These are independent. That's what IID means. So it's about
Oh,
samples, not about some two distributions. Okay.
okay. Yeah.
Okay. Okay.
Mm.
So now here in this case, what we are given is this joint is there and we are given samples. One of the realization of these samples, right? So this is one data set which has been given to us, right? This is just one realization of the m set of samples, right? Okay. So now the question you should ask is, if these are IID samples from this distribution, then can I consider ym to y1 to ym as IID samples for this distribution? If so, then I can use the existing ideas I have for parameter estimation to estimate the parameters of the corresponding Bernoulli model. Is this point clear? So this is the right question perhaps you should have asked. If it is any question related to IID, this is one of the questions perhaps you should have asked. Okay. What is the question? I currently know that x1 comma y1, these things are IID samples from this distribution. Now, later on, what will I do when I do modeling? Sometime I will have to estimate parameters of this Bernoulli. Sometimes I have to estimate, at some point of time, I will have to estimate, the mean and covariance of this, the mean and covariance of this. Now, how will I estimate all of this? I can't estimate unless I am given samples. Now, there are no more samples than those given in the training set, right? So I should reuse the samples from the training set. So now the question is, which samples will you use for estimating Py? The obvious choice is the values of the outputs. Then one question perhaps which you can ask is this set of samples IID from this distribution? That's perhaps a valid question. So do you guys understand this question?
Yes, sir.
Okay. Now once you ask this question, it is easy to show that it is IID because you are saying x1 comma y1 is generated from p star x comma y. So definitely y1 will be generated from p star of y. Okay, so that's not a problem. So all these are identically distributed. That's very clear. Secondly, I am given that x1 comma y1 to xm comma y1 are mutually independent, right? So by the definitions, by the properties of independence, you can also show that y1 to ym will be mutually independent. Okay, so this is a property of mutual independence. You can go home and verify this. Okay, if these are independent mutually, then you can show that these are independent. Okay, but not the other way. Okay. Okay, so that can be shown. Now that's okay. That's why these samples are IID samples from P star Y. If they are IID samples from P star Y, we already know how to estimate Bernoulli parameters, right? How will you estimate? For example, I'll say the true probability of taking the first class is estimated as the fraction of examples in my training set that are of first class. As simple as that. Okay. So Bernoulli estimation is clear, right? Now, how will you estimate P of x given 1? Again, you have to use training data, but which part of the training data will you use?
Where label is 1.
Very good. That's all. So you'll take all x's, xi's such that xi comma 1 is the training set point, right? So you'll take all such points. There may be many points. So these are all the positively labeled or class 1 labeled points of the training set, right? Now it's an exercise to show that those will be IID from which distribution? They'll be IID from this distribution. Okay. So sorry, this is not the IID sample. Such x's. So I'll take x I belongs to P. They are IID from this, where P is the set of all indices for class 1 samples. Okay. So note that xi comma 1, that's not IID from this distribution, because this distribution only outputs elements of the form x. This is like x comma 1, so this cannot be generated from x given 1. So the corresponding samples, the corresponding inputs alone, those will be generated by this. You can show that they are IID samples from this distribution. Okay. Similarly, so if you know this, you know already how to estimate the multivariate Gaussian. Similarly, you will take only the points from the negative class or whatever the second class, and they will be IID samples from P star of x given 2. Okay. So go home and try to show these exercises, right? If x comma y are IID samples from the joint, then the class 1 labeled training inputs will be IID from this distribution, and the class 2 labeled training inputs will be IIDs from this distribution. Okay, and hence you can estimate the parameters. So step 1 clear for everybody?
Sir, what about the denominator in the posterior calculation?
Right. Posterior calculation, the denominator is P star of x, but that's nothing but P star of x can be got by marginalizing this over y. That's what we are doing here, right? So this is called total probability rule. This is called total probability rule. Okay. So P star of x can be obtained like this. But as we will see later on, I mean, we always need only the form of the, P of y gamma x, y given x. What is P star of x? It's just a normalization constant. So you can retrieve it anytime. You don't need to actually compute it. Okay. So you can, if you are lazy, you can just ignore P star of x. But if you want to compute the total, I wrote the formula, right?
Okay.
Okay. So any other questions, please, in the first part? So the first part, let me revise what I did in classification. The first thing we figured out is there's no explicit model we know of that outputs some real numbers and some discrete values simultaneously. So there's no way I can explicitly model the joint distribution in case of classification. So the obvious thing to do was think about implicit ways of modeling the joint, and the natural choice was modeling the prior likelihood of the outputs and the class conditional likelihoods of the inputs. So the first step was to model the
I am unable to hear anything. Are others able to hear?
No, I guess sir got dropped off.
Okay.
Yeah, I'm also not able to.
हम बता रहे 4:45 हैं?
hello.
Yes, sir.
Yes, sir. We are able to hear you.
You are able to see the screen also?
No, sir.
No, sir.
Now?
Yes, sir. Yeah.
Okay, so I was just trying to revise what we did till now in classification. So I was saying that there's no way to model the joint distribution directly, because the joint distribution will take values which are real numbers and discrete numbers simultaneously. So the way out was an indirect way of modeling the joint. We modeled the joint using three distributions. One is the prior likelihood of the outputs, that's P star Y, and then two class conditional likelihoods of the inputs, right? And the class conditionals we modeled using Gaussian, and the prior we model using the Bernoulli, right? And once the modeling was clear, the parameter estimation was very simple, because we already know the details of parameter estimation with these things, right? Okay, so after the first step, what do we have? Because of this indirect modeling, whatever we did, we actually know what is the final thing that we know after the first step. So after the first step, we know two things. We know x given y for each y, and we know p hat of y. Okay, both. Now what is the second step? Second step is to compute the posterior, and that's given by Bayes rule that we already. So this is proportional to p hat x given y, p hat of y. Now somebody was asking what about the denominator? Denominator, I can always have the formula, or I can ignore it as a normalization constant like I did it here. Okay. So now let's do the following. For the case of our model, let's try to write down the form of the posterior. Okay. Now what will be the form of the posterior? This is proportional to e to the power of. So let me call the parameter of the Gaussian as mu y comma sigma y. Okay. So what is mu y? It is the yth class mean. And what is sigma y? It is the yth class covariance. Okay. And what are the values y takes? 1 and 2. Okay. And the parameters of the Bernoulli, there is only one parameter. It's pi. Let me call it by pi. But let me call pi 1 as the probability of first class and pi 2 as probability of second class, just to. Okay. So similarly here there is mu1 sigma 1 and mu2 sigma 2. Okay. Okay, this is our notation, and all these are hats. Okay, so I'm just okay. If this is the notation, what is the likelihood of x given y? Can anybody tell the formula for it? Is e to the power minus half. What should I write here? So I'm writing the likelihood for x given y. Who will help me?
X minus mu1 whole square.
X minus mu1 or mu y?
Mu y.
Mu y, right? Okay, mu y whole square. Are you sure? X is a vector. What do you mean by square of vector? So it's transpose, right?
Yes, sir.
So then, okay, I'm only writing. So this, right? Yes, no?
Yes, sir.
Yes, sir.
Okay. Into py. Py we are just calling. So if it is class y, it is pi y, right? Okay. Now this is also proportional to e to the power of minus half. I'm just writing this part of the quadratic in x, right? Plus log y, just for log pi y. So this is clear. So what about the normalization constant? This is a Bernoulli. Normalization is very easy. You just divide by the same term, sum of all the terms in the numerator, right? So that's very clear. So the posterior form is clear to everybody?
Yes.
Okay. Now I'll ask you a question. Can you describe, posterior of the four models which we know of? Which form of the distribution does the posterior follow? There are four named distributions we know, right? Bernoulli, multinolli, univariate, multivariate, Gaussian. Of these four, the posterior in this case follows which distribution?
Distribution is Gaussian.
Gaussian distribution.
Gaussian. Why given x? That's why I asked you this question. See, all these questions have simple answers, but because of x, y, invariably you guys will get confused. So you should always think and answer. So let me repeat the question. What is the distribution form, likelihood form, named likelihood form of the distribution in the posterior, which is being shown on the screen? So you guys are not thinking.
It's Bernoulli only, right?
It's Bernoulli. Why should you take so much time? Because the values y takes is still two discrete values. How can it be Gaussian or multivariate Gaussian? So you should not look at x. No, x is given here. The distribution is over y. So what values of y are being taken, right? Is this clear to everybody? So whatever I wrote here, the formula here, just because something has e to the power of, don't call it Gaussian. It depends on what is the random variable, right? So here in this, so okay, so in this, I think we are already zoomed in, that's why this is okay. So this fellow is not a Gaussian distribution because it's not a Gaussian in y, right? It may be a Gaussian in x, who cares? X is given. So this expression actually is what? A Bernoulli distribution in y. Is that clear to everybody?
Yes, sir.
Yes, sir. Yes, sir.
So then tell me what is the parameter. If I have to use the notation, like previously we said the posterior was normal. In the case of regression, we wrote like this, no? Then we wrote the mean and the variance. Like that, if I have to write such a notation, if I have to write Bernoulli, then there is only one parameter, right? What is it? It's the probability of 1, class 1. Can anybody tell me what is the expression for that? Again, I know this is a simple question, but this is just to verify whether you understood. So let me call it as theta. Can somebody tell me the value of theta?
Pi y.
Huh? Pi y. Okay. But this will be a function of x. If it is pi y, then I didn't learn anything, right? If it is pi y, I am saying the posterior distribution of outputs is same as prior distribution of outputs. Sophia, am I wrong in saying this?
Yes, correct. I got confused.
Right. Now can you update and tell me what is theta x?
So mu y you'll replace by the probability of that class.
So
No,
pi
I still have
1
to think.
Yeah,
pi
anybody?
1 raised to power x, pi 2 raised to.
See, it is sitting here. I just wrote it. So this is all. That's all you have to say. So theta x is simply this, no? So this is the probability of y. So you just have to substitute 1 there. So I told you what is y given x. You just have to substitute 1 given x, right? That is the... Everybody agrees? See, I gave you an expression for y given x. But what is the parameter value in case of Bernoulli? It is a probability, likelihood of 1 given x, no? It's a probability of 1. Yes or no? So I just have to put y equal to 1. That's all. So it is this. So you guys are not focusing. So this is what I'll get. 1 inverse x minus mu 1 plus log pi 1 by what? Just the normalization, right? So that's the only thing missing. So it's the same thing. So probability of class 1, that is this score, whatever,
Sir,
plus for 2. Yeah.
What is mu y here?
Okay, I'll come back just a minute. Let me finish this. And minus mu 2 plus log pi 2. So what is mu 2? Let's go back. So what is mu 2? It is the parameter for the Gaussian that models x given 2. This is x given 1. So you take all the points labeled as 2 in your training set and compute the sample mean and sample covariance. That is mu 2 sigma 2.
Okay, got it.
Okay. So similarly mu 1 sigma 1. So get those mu's, get those pi's. What is pi? It is a fraction of points labeled as class 1 in your training set. That's all. Okay. So get those things, place it in this formula. That will give you the parameter of the Bernoulli. Is that clear to everybody? Now is it clear?
Yes.
Yes.
Yes, sir.
Okay, good. See, here is another way of understanding this. See, the posterior is a Bernoulli, that's very clear. but the crucial question is which function of x is the parameter. The parameter x, the parameter is a function of x which is guaranteed to be positive here, right? First of all, because it's e to the power of some value, and it's e to the power of some quadratic function of x. That's the kind of relationship, you know, the parameter has as a function of x. Now, does anybody recall the relationship of parameter with respect to x in case of regression?
It's
Classification.
linear.
It's a very good. It's like a linear function, right? Linear function with a constant term. So something like a linear function, right? We already said linear and affine functions are same, right? Some classes back. Okay. So anyway, that was the relationship. Here, what is the relationship? It is not linear function. It is e to the power of some quadratic function. Okay. So that's how. Okay. So is this clear? Why e to the power of came? Because first of all, theta is always positive. So, you know, you can't write their linear function or quadratic function, because quadratic function, linear function, these things can take negative or positive values. So e to the power of linear is a better choice, right? But unfortunately here it's not e to the power of linear, it is more complicated, it's e to the power of a quadratic. Now, why did the quadratic come? Because you modeled the class conditionals as Gaussians, right? Again, in this case, the form, okay, let's write down. So the posterior, is it clear? The discussion on posterior, is it clear? Very simple derivation. Okay, so now what is the third step in generative modeling? Third step, please.
Register.
Yeah, Kali register, but in this case, what is it? For classification, what is it? For classification, what is it? Is it the mean of the posterior?
Mode, right?
Mode, right?
It's the mode, right? Very good. So mode. So what is mode? The how do you compute the mode? It is the most frequent value, right? So in other words, you have to see whether theta is greater or 1 minus theta is greater. Which one is greater? That's what you have to see, right? What is 1 minus theta? It is the probability of class 2. What is theta x? It is the probability of class 1. Which one is greater? If this happens, then you will call it class 1. If the other way it happens, you will call it class 2. Yes or no? That's the mode. See, if probability, if theta x is greater than 1 minus this, what does it mean? It means probability of 1 given x is greater than probability of 2 given x. In this case, what is the mode? If this happens, what will be the mode? 1.
1.
Right. That's all I'm saying. So what is the function? This is 1 if theta x is greater than minus 1 minus theta x, right? So in other words, what should happen? This quantity should be greater than this quantity. That's all, right? Okay. Now e is a monotonic function, so I can simply compare the exponents instead, right? So I can just say if minus half x minus mu1 transpose sigma 1 inverse x minus mu2 plus log pi 1 is greater than minus half, again the same thing for the second class. Okay. Sorry, this is mu1. Okay, and then 2 otherwise. So is this function clear?
Yes, sir.
Okay. So any doubts in the derivation of the generative model for classification. By the way, this generative model for classification is called as the Bayes classifier. Again, I know it's a confusing name. It should not be confused with Bayes optimal. Okay, this is called Bayes classifier because in the crucial second step, you use Bayes rule to compute the posterior. Okay, that's why it's called Bayes classifier. Okay. Okay. So Bayes classifier model, and the final function g hat is called the Bayes classifier. Bayes classifier. Okay. So are there any doubts in Bayes classifier model or in Bayes classification model in the
Sir,
derivation?
does naive Bayes classifier
Yes,
means the same
is
thing?
related to this. No, it doesn't mean the same thing. It's a special case of Bayes classifier. Okay.
Okay.
So this model with some more assumptions is same as naive. Okay. Bayes. What are those assumptions? We'll come to them later. Okay. Perhaps when we do sequence modeling, or I don't know, whenever possible, I'll cover that. Okay.
Okay, sir.
But it is definitely related to this. It's a special case of this. Any other doubts? Okay. If not, let's try to give a visualization how all of this looks like. Right. Now, suppose I am in 2D. So my x is R2 and I have a binary classification problem. Okay, so this is my first factor, first attribute, second attributes, first feature, second feature, and we already visualized how Gaussian distributions look like, right? So let's imagine this is mu1, and this is how the covariance of mu1 sigma1 looks like. So this is how the distribution. So it's a 3D bell curve whose contours I am drawing. Okay. Okay, so that's class 1. Similarly, let's assume that this is mu2. Okay, and there are some other shapes. So this is, okay, so some other shape, sigma 2, but this is more concentrated, right? So this, so the concentric ellipses are close by in this case than in the other case. So it is a highly density, a highly pointed bell curve than the other one. So the other bell curve is more flatter. Okay, so let's consider this situation. So what is this? This is P of x given 1, that's the visualization, and this is P of x given 2, that's the visualization. Okay, and how will my so then how will you visualize the classifier? One way to visualize the classifier is the following. So people typically, when they do classification, when they want to visualize classifiers, they do the following, especially in case of binary classification, right? They mark out which regions have exactly an equality here. So basically they draw the surface at which both classes have equal probability. That's basically an equality here, right? So if this is greater than, strictly greater than this, you will call it 1, right? So all x where this is less than this, you will call it 2, right? So you will try to plot the cases, the all x, locus of all points, locus of all x, where probability of 1 given x is equal to probability of 2 given x. That's called the discriminating surface. That's called the discriminating surface. Okay, or classifier surface, classification surface. There are many names. Okay, so let's plot that surface in this case. First of all, how will the plot look like? Will it be a linear curve? Will it be like a line?
It will be a plane.
No.
It'll be a quadratic curve.
Very good. So it's a quadratic expression, right? So this minus this is equal to 0. This is one quadratic, this is another quadratic. So it's some quadratic minus some quadratic, other quadratic is equal to 0. This is how it will look like. And in the general case, q1 minus q2 will be a quadratic. Right? So in the general case, this may look like this. The locus of all points may look like some curve like this, a quadratic curve. My quadratic is a very bad. So let me just try to draw some quadratic. May not be a quadratic, but something like this. Okay. And what will happen with pi? So if you have pi 1 more than pi 2, but everything else same, the same shape remains and the classifier keeps going to the side of what? Side of 2. Because P1 is greater than P2. If you keep on increasing the prior of 1, more and more points get classified as 1, right? So this is if P1 increases, prior increases basically. But the likelihoods, class conditionals remain same, then this will not happen. The shape will remain the same, but only the shifting will happen because these are coming as the constant terms in the quadratic. Right? Okay. So ultimately, if you give 0 prior to class 2, then independent of the class conditional, you will say all points are 1. Right? So that's a danger anyway. So fine. And what will happen if there are some special cases, right? For example, if sigma 1 is equal to sigma 2, then what will happen? Can anybody tell me how this q1 minus q2 will look like? Will it still be a quadratic surface? What will happen if sigma 1 is equal to sigma 2?
It will become a linear surface.
Very good. The quadratic term x transpose sigma inverse x, that cancels out. Right? So it will become a linear surface. Right? So this is the corresponding visualization. So if you have a case where it's equal covariance, so how will equal covariance look like? Maybe some case like this, mu1, and this is the shape of the covariance, and this is some mu2, and the shape remains same. That's what sigma 1 equal to sigma 2 means. Okay. Then what will happen? Then there will be a line that separates. Okay, that's the, and if the prior of 1 increases, the line shifts towards this side. So this is if prior increases. Okay. Okay. So okay. So is the visualization clear to everybody? So because this discriminating surface is quadratic, sometimes this base classifier in the special case. By the way, base classifier name is correct irrespective of whether I use Gaussian here or not. Sometimes I may use some other distribution. Even then you will call it Bayes classifier. But Bayes classifier with Gaussian class conditionals, that has a special name. You sometimes people call it as quadratic discriminant analysis or Gaussian discriminant analysis. These are the various names in your books. Okay. So this is nothing but Bayes classifier with class conditional as Gaussian. Okay, that's how this name comes. Okay, and in this special case, it is called linear discriminant analysis. Okay, there is another LDA also which people do in machine learning, quite popular, which is not this. You should not confuse that LDA with this. Okay, so any questions in Bayes classification?
Sir, I'm trying to understand, like, when the prior of 1 increases, how does the line move? Could you just explain me again?
So see this, if prior of 1 increases, what will happen to this term? This minus this, that will keep on increasing, right?
Yes, sir.
So it's like the same. So it's like W transpose X minus, B equal to 0 was there previously. Now it will become W transpose X B minus 1 is equal to 0, minus 2 is equal to 0, something like that, right? So it keeps on shifting towards one side. If B changes to B plus 1, if B changes to B plus 2, then this is what will happen, right?
Yes, sir.
That's all I'm saying. Yeah. And which side it will move? It will, if prior of 1 increases, then of course more and more points will be classified as 1. So it will move away from the 1 distribution, right? That's all I'm saying. So is this clear? How pi is playing a role, prior is playing a role?
Yes, sir.
So prior, in essence, what I'm saying is prior does not change the shape of the surface. It only shifts the surface. Whereas the class conditionals, they determine the shape. They don't determine the location. Okay. So prior determines the location and shape determines the, the shape is determined by the class condition, something like that, right? Okay, class condition also decides the location also, but primarily it's controlled by the prior. Okay. Any other doubts, please? Okay, so what did we do in this lecture? We derived, we based on the learning from the previous class, we built generative models for regression and classification. In the first case, we got very, analogous results to linear regression. In the second case, we got a completely new kind of classifier. This kind of classifier we have never seen before, because it is like classifying with quadratic surfaces, right? So that was the difference. But in the special case, in some special cases, it again turned out to be similar to linear classification. So in terms of the models used for Bayes optimal, perhaps these generative models are similar to the corresponding non-probabilistic models, but the parameter values that are used may be completely different, right? So that's what this whole thing is telling. And in some cases like this, generative modeling may give completely different models than what we know in what we studied in non-probabilistic models previously. Okay. Anyway, so so if all of this is clear, we can stop here. What we'll do in the next lecture is we'll cover discriminative models for classification and regression, right? That's what we'll do in the next lecture, and
Sir,
that will finish the first part of this course. Yeah.
sir, I have one question. So,
Yeah.
can we just use that the final that quadratic QD as a discriminant function? Is it?
Right. So this is the final function, right? So this is the base, our approximation to the, yeah, this is the base classifier. Yeah.
No, like what I'm saying is, if we we can, this can also be just a discriminant function, right? We are just comparing the distance towards the two clusters and seeing if that distance is and then we are saying that we'll assign it to cluster one if it is more than the
Right.
distance
So
to cluster two.
if you want to use the terminology which you are using, yes, that intuition is correct. But none of this terminology we have talked in this lecture. But yes, you are right. I mean, I never introduced clustering. I never introduced other terms. So, but you are right. Yeah. So, any other comments or? Observations or okay, good. So in the next lecture we'll try to discuss discriminative models. Okay. So we'll stop here.
Thank you.
So how many of you have attempted exam 1? All of you?
Not yet, sir.
Yet to attempt, sir.
Okay. So please first go through the syllabus. Prepare as if you are writing an exam. So first 6 lectures, that's all, in the lecture notes. Right. So basically, before everything, till the start of probabilistic modeling, that's what is there. So the entire non-probabilistic modeling or entire ERM, that's what is there for the portion. So prepare well, do the practice problems, and then attempt the exam 1. Okay, as if you are in an exam hall, respecting the time constraints, everything. And then you evaluate yourself. Most importantly, after all of this, so doing all of this actually is more important than all of this is once you attempt the exam, please go through the solutions very carefully and try to understand why you have not thought about the solutions in that way, or why should your solutions be also correct, right? So these kind of things raise concerns or discuss with me whenever possible. Okay, so unless you so each question, each example you do matters, right? So there are a limited set of examples. So the ones in the book or in the practice problems or in the exams, whatever, they are limited resources, right? So each example should give you a lot of learning. So please attempt them with full interest and try to seek the answers whenever possible. Okay, so with that note, let's call it a day.
Sure, sure. Thank you.
Yeah, thanks. Bye.
Thank you, sir.
Sure, sir. Thank you, sir.
Thank you, sir.
Thank you.
Thanks.
networks which is available in mobile. And another issue is the same network may be advertised by